Okay. 6.2 is electric forces and fields. The portion 6.2.1 and 6.2.2 and 6.3. These have to do with static charges and properties of conductors and insulators. A lot of students, they don't, when you have a question in the exam based on this part, the initial portion will usually have questions based on static charges, conductors and insulators. A lot of students tend to not like to answer those questions, simply getting put off by that portion. The reason is because this is a bit of, it's a bit theoretical and a bit of memorization, or rather a little descriptive in the exams rather than numerically solving it. So, but here's the thing, the rest of it would be very easily done because the rest of it is basically numericals. Only thing is that they need to get over the hurdle of answering this small portion or the small chunk on static charges. So, about static charges. Firstly, they should know that these are very basic concepts. There are two types of charges, positive charges and negative charges. Well, when we say that a material is positively charged, we are not talking about the movement of positive charges, but rather a deficiency of negative charges. So they should firstly understand that the only charges that move are electrons. Okay, electrons are mobile charges, mobile charge carriers. Okay, now they are negatively charged. So, for example, when you have a perspex rod, okay, if you have a perspex rod, which is an insulating material, and a silk cloth, okay, if you rub these two together, you will find that the silk cloth will become negatively charged, and the perspex rod will be positively charged. What this simply means is that when they were rubbed together, the electrons on the surface of the perspex rod were transferred due to friction onto the silk cloth. Now, the positive charges don't move. That's the most important thing. Okay, so they should know of a few examples of what when it undergoes friction with what kind of material, what kind of charges would be produced. Okay, so this is one example. They should also know that negative charges, like charges would repel each other and unlike charges would attract each other. Law of conservation of charges. So let's say 16 units of positive charges were developed here. There would also be 16 units of negative charges developed here. The law of conservation of charges states that in a closed system, the total number of charges would always be constant. Okay? So there will not be any charges developed or removed within a closed system. Okay? 6.2.3 is basically describing the difference between conductors and insulators. The basic concepts are the same as what we've learned before. Conductors have mobile electrons which can carry charges, whereas insulators do not have these mobile electrons to carry charges. How it's relevant here is when you have an insulator and you charge it, you are able to hold it and accumulate charges on it. Why? Because the accumulation of static charge is possible in insulators because they do not flow through the insulator due to the lack of mobile electrons. Whereas a conductor cannot have static charge accumulation because the charges will continuously flow through them due to the presence of mobile electrons. And let's say I'm holding a conductor, the charges will flow through this and get earth through my body. So that's the initial portion, which is a little descriptive in the exam situation. 6.2.4 onwards is simply talking about electric fields and forces, which is extremely similar, which is very similar to gravitational fields and forces, except for one fact, that the forces can be either attractive or repulsive. Whereas in gravitation, you have only attractive forces. So, just like in gravitation, when you have two charged objects, okay, or 2 point charges, you have a force of, you have a electric force in between these two charges, and which is proportional to the product of their charges, and which is inversely proportional to the square of the distance between their centers. Okay, so very similar to gravitation. Now this proportionality can be removed by a constant, okay, and this constant is called the Coulomb's constant. Coulomb's constant. Okay, so Coulomb's constant should be given in the data booklet. Okay, this Coulomb's constant is actually equal to a value of 1 over 4 pi epsilon naught, where epsilon naught is the permittivity constant of free space. So they don't need to know this in great detail, but if they're interested, they should know that permittivity is basically, it basically means that they're assuming that in between these two charges there is free space, and the permittivity is a factor which shows or which determines how easy is it for the electric forces to travel between the medium in between these two charges. Okay, so for all purposes in IB, the medium is always considered to be free space. Okay, now so this is the electric force. Now remember, what we are talking about is simply the magnitude of electric force. In an exam situation, whether this force is positive or whether this force is attractive or repulsive will depend upon whether these charges are like charges or unlike charges. So it's always it is always recommended to calculate the magnitude of the force separately and determine the direction separately. So I'll try. Okay, in a previous part we had started off with Coulomb's law in 6.2.4. So we had determined that the electric force between two charges is given by k q1 q2 over r square, where k here is the Coulomb's constant. The value of k can be determined by this 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Okay, so an important note was that in an exam situation, the students must calculate the magnitude of this force separately and determine the direction separately based on whether these are like charges or unlike charges. Now, for example, if this was a positive charge here and a negative charge here, okay, and if I wanted to determine the force on charge Q2 due to charge Q1, I would know that since these are unlike charges, the force will be an attractive force, okay, and this force will be, the magnitude of this force will be determined by this value, okay. So that's the electric force. Now, just like in gravitational fields, in electric fields we have, if you want to standardize the strength of electric field at a certain point, what we do is, in gravitation we placed a unit mass at that point in the field, and we saw what was the force acting on that unit mass. That would determine the gravitational field strength. In electric fields, what we do is, we have to place a unit charge, just like in gravitational fields. But in this case, the question arises whether it's a negative charge or a positive charge. So to standardize, what we use is a unit positive charge. So we will place a unit positive charge at a point in the field and see what is the force on that charge.